The nature of gases. Kinetic energy is energy of motion, and all gas particles, whether they are molecules or atoms, are in constant motion. So all gas particles have kinetic energy. We're going to look at something called the kinetic theory of gases. There are three assumptions that are made, and I want you to know these three assumptions. Number one, the particles in a gas are considered to be small, hard spheres with an insignificant volume. Gas particles are relatively far apart because they spread to fill their container, and no attractive or repulsive forces exist between particles, so those particles move independently of one another. Number two, the motion of the particles in a gas is rapid, constant, and random. They always fill their containers, and they will travel in straight line paths until they collide with something. Number three, all collisions between particles in a gas are perfectly elastic, which means kinetic energy is transferred without loss from one particle to another. Gas pressure. Pressure is defined as the force exerted per unit area. So pressure is force over area. Now, gas pressure is the result of collisions of billions of rapidly moving particles in a gas with an object. Atmospheric pressure results from the collisions of atoms and molecules in air with objects. I like to think of atmospheric pressure as the pressure that is pushing downward on us. And atmospheric pressure is measured with something called a barometer. So here's what a simple barometer looks like. Atmospheric pressure pushes down, and as atmospheric pressure pushes down in this tub of mercury, some of the mercury goes up the glass tube, and you notice that there is a scale on that glass tube, kind of like a thermometer, with increments. And we can read the atmospheric pressure on that scale in terms of millimeters of mercury. So atmospheric pressure pushes down, it forces the mercury up the glass tube to where the atmospheric pressure supports that column of mercury. And we read it in millimeters of mercury. Here are some units for pressure. We have the Pascal, which is the SI unit. We have standard atmosphere, which is a common unit. And we have millimeters of mercury, which is also a common unit. You need to know these conversions. 1 atmosphere is 760 millimeters, is 101.3 kilopascals, which is 101,300 pascals. So know those conversions between pressure units. Let's look at a couple examples. I have a gas that's at 385 millimeters. I want to convert 385 millimeters to kilopascals and atmospheres. Let's first go to kilopascals. Go back to your unit conversions. There are 760 millimeters for every 101.3 kilopascals. So in kilopascals, 51.3 kPa. And then if I want to go from millimeters of mercury, 385, to atmospheres, you can go back to those numbers. There are 760 millimeters for every 1 atmosphere. So in atmospheres, 0.507. By the way, normal atmospheric pressure at sea level is 1 atmosphere. And in Cape Girardeau, we're under atmospheric pressure of about 1 atmosphere. Example number 2, the pressure at the top of Mount Everest is 33.7 kPa. I want to go to atmospheres because I want to know if that's greater or less than 0.25 atmospheres. As you increase elevation on Mount Everest, the atmospheric pressure decreases. So we want to go from kPa, and the conversion is 101.3 kPa, to atmospheres, it's 1. So on the top of Mount Everest, our atmospheric pressure in atmospheres is 0.33. And again, normal atmospheric pressure is 1 atmosphere, but as we increase elevation, the atmospheric pressure decreases, so 0.33. As a substance is heated, its particles absorb energy. Some of this energy is stored as potential energy, but some speeds up the particles or increases the kinetic energy. Now, the increase in kinetic energy results in an increase in temperature. These two are directly proportional. If kinetic energy goes up, temperature goes up. If kinetic energy goes down, temperature goes down. So they're directly proportional. Atoms or molecules at a given temperature have a wide range of kinetic energies. Some have really low kinetic energies, some have really high kinetic energies. But most have kinetic energies somewhere in the middle. So we're going to use the term average kinetic energy to describe these particles. Now, at a given temperature, here's an important piece. At a given temperature, the particles of all substances, regardless of physical state, have the same kinetic energy. So at a given temperature, you could be a liquid, a solid, or a gas. You would have the same average kinetic energy. So again, temperature and kinetic energy are directly proportional. Let's look at a graph of percent of molecules versus kinetic energy. So we have percent of molecules over here. We have kinetic energy on the x-axis. We'll do a cold temperature, and we'll do a warmer temperature. So here's my cold temp up here, graph. Here's my hot temp down here. Okay, let's look at the cold graph first. And here's what I mean in terms of percent of molecules versus kinetic energy. Some of the molecules at the cold temperature have kinetic energies way over here, low kinetic energies. But even at a cold temperature, some molecules have a kinetic energy way over here, very high kinetic energy for a cold temp. Most of the molecules, though, are going to be right here at the peak. This is my average kinetic energy at the peak. All right, let's look at the hot temperature curve. Even in hot water or a hot temperature, some molecules have a very low kinetic energy. Some molecules are going to be way over here at very high, but most of the molecules in the hot temperature are going to be right here at the peak. So my average kinetic energy falls right there. So notice what's happened. As I increased the temperature, I went from cold to hot, the average kinetic energy increased as well. So kinetic energy, temperature, directly proportional. Particles would have no kinetic energy at 0 Kelvin. That is absolute zero. At 0 Kelvin, all motion ceases. The Kelvin temperature of a substance is directly proportional to the average kinetic energy. So we do not use the Celsius scale when we compare temperature to kinetic energy. We use the Kelvin scale. And to go from Celsius to Kelvin, we simply add 273.